Okay, we're back again, and today we're going to look at simple machines and a concept that's called mechanical advantage. Mechanical advantage. And what this simply means is that we use simple machines to give us an advantage, to make our lives easier for us. And if we take a look at some of the simple machines that we've already looked at, well, we have the lever. And of course, the lever allows us to lift objects with a force that is smaller. If we push down here with the effort force, it is a smaller force than the weight or the load force of this rock. And the reason is because levers make use of something called torque. And the torque of the effort force has to be the same as the torque of the load. We've already talked about this. And we said that the effort force multiplied by the distance of the effort from the fulcrum, which in our picture is this distance right here in purple, that would equal the load torque, which is the force of the load multiplied by the distance that the load is from the fulcrum. And I'll put that in red. Actually, I'll use different colors. Say green. How about blue? That's the distance from here to here. Now, just without using any numbers, you can look at the picture and you'll see that what we can do is use a smaller effort force that I wrote in red, multiply it by a bigger effort distance. And if you multiply a small number by a big number, you can get the same effect if you use a larger load force, but counteract that with a tiny or smaller effort distance. So you can get the same product, okay? The same product. And so what we're doing is on the effort side, we're making it a smaller force, but a longer distance. So you can see the effort is here. It's a smaller force than the green load, but look at the distance. It's longer. And on the load side, you can see that the load force is a little bit heavier. The weight of the rock is more. Because you know what? If the weight of the rock wasn't so big, we wouldn't need a lever. We could just lift it up with the effort of our arms without a lever. But if our arms are weak and we cannot lift the rock, we can use a smaller effort force if we have a bigger distance. So here we have a larger load force but smaller distance. So they still work out the same. So what's actually happening here is we are trading. It's a trade-off. If you want to lift something heavy, you can get away with a smaller force if you use a longer distance. So it's a trade-off between force and distance. And what we'll see in all of our simple machines that we discuss is that this trade-off will happen. All right? Okay. Now, if we consider the what we call the mechanical advantage, that's basically showing us what advantage we can get out of a machine like this. In other words, how much is the lever really helping us? That's kind of what we're after. Okay, so let's look at what happens with our little ratio here. If we take effort force times effort distance, and we say that equals load force times load distance, that's what we had up above, I can rearrange this equation in a number of ways. I can divide both sides by the load force and at the same time, or the effort force, either one, and I could rearrange the equation. If I divide both sides by FE, and at the same time, I divide both sides by RL, here's what I can get. I can turn this into FL divided by FE equals RE divided by RL. RE over RL is the same as FL over FE. And that's just by dividing things around. Now what I want you to realize is what we have created are two ratios. This one is a ratio of forces. And then the other one is a ratio of distances. So let me pick another color here, green, and let me go here and show you the ratio of distances. Okay. These two ratios are important because they can help us determine what the advantage is of using one of these, say, these levers that we've been talking about. Now, if we take the, I'm going to write it in green here, if we take the ratio of distance, the ratio of distances, and you'll notice that it's kind of, these two are sort of upside down to each other. One has the effort on top and the load on the bottom. The other has the load on the top and the effort on the bottom. So you have to be careful. The ratio of distances is equal to the effort distance divided by the load distance. We call that the ideal mechanical advantage. And the reason it's ideal is because nothing can really affect the distances. If you build a lever, those distances are always going to be what they are. You can't change that. Now, there is a little bit of a problem though. When you actually start to apply force to a lever, there is something that can be changed. So let's look at the force ratio. The ratio of forces, which is upside down, you'll notice. It's upside down. It's the load force divided by the effort force. This equals what we call the actual mechanical advantage. So depending on what the question you're dealing with is looking for, you may have to use one or the other. Now here's why this is different. In any kind of machine, there's going to be some loss of force. When you have a lever, the lever, for instance, if I draw a couple of pictures here to help you, the lever that you have will be, let's say here's a lever, and here's the fulcrum. Well, when you push on this, perhaps the board is not perfectly rigid. Maybe the board would bend a little bit as you pushed it over the lever. That bending is going to take away from the lever's ability to do its job. It's going to make you actually have to push a little harder. There could also be some problem with the fulcrum. Maybe it's not sitting very well. Maybe the board bounces or bumps on the fulcrum. There are lots of reasons why the effort force would not be perfect. It's very hard to get a board, even a thick metal rod will still bend a little bit if you put forces on it. And so because you don't get this perfect situation in real life, because nothing is perfect, the actual mechanical advantage you get will always be less than the real mechanical advantage. So let's do a couple of simple examples with a particular lever. Okay? So let's say we have a lever. I'll draw it here. Put a fulcrum. Let's say we have a load. We'll put a big rock on the end. And that load will have, obviously, a weight. And we'll say it's 700 newtons. Okay. And we can put in some distances. We'll say that this distance here is 1 meter. And we'll say that way down here at the end, where you're going to push, right over here, that looks like about 2 meters. Good. And we'll put in an effort force. You would have to raise the rock, you'd have to push down on this, say that's the effort force. Now, if the lever was perfect, we could do our calculations, and we could figure out what that effort torque was needed to be, right? So let's do that. Let's do the torque at the effort is equal to, whoops, not equal to, oh yeah, that'll work. Effort torque is equal to load torque. Effort torque is force of the effort times distance of the effort, and that equals the force of the load times the distance of the load. And if we put the numbers in, I'll just move over to the side. The force of the effort is what we're looking for, but we have the distance to the effort is 2 meters, and then that would equal the force of the load, which is 700, and we would multiply that by 1. So we get Fe times 2 equals 700. And if I divide both sides by 2, the effort force is equal to 700 divided by 2, which is 350 newtons. Okay, good. So let's just do our mechanical advantage. The ideal mechanical advantage, which we often just shortcut to IMA, is equal to the ratio of distances. And you'll remember it's the effort distance, RE, divided by RL. If we go up to our definition up here, there it is, right there. That's the ideal mechanical advantage. And we can calculate that. We can get a number because it's very simple. Look at the two distances we have, a 2 and a 1. Effort distance is 2 meters, and the distance of the load is up here, 1 meter. So if we do that, it's 2 over 1, which means it's 2. So that tells us that every effort newton we're putting in is lifting 2 newtons of weight. So it's doubling our efforts. And if we do the AMA, the actual mechanical advantage, we would get something that says the, whoops, I'm writing the wrong number. We would get the force of the load, remember it's upside down, divided by the force of the effort. And in our case, the force of the load was the weight of that rock, 700 newtons right there, and our effort force we calculated to be 350 newtons. So we would put 700 for the rock, 350, and if you divide 700 by 350, you get 2. So they look like they're the same. But here's the problem. This is only on paper. In real life, that lever would bend a little bit, and it would cause us to require more force. So 350 newtons of effort force wouldn't do it. We would have to add force to make up for the imperfections in the board and the imperfections in the lever. So the real true answer, if you were to do it in real life, not just calculating math, but if you were willing to push, you might find that it actually takes 380 newtons of force instead. Now you can't really calculate that, you have to measure it by doing the experiment in real life. So let's say it took 380 newtons extra. Well, then you can see that your actual mechanical advantage would change. If we do it again, but with a load force and an effort force, this time 700 newtons of weight, about 380 newtons. Well, if you pull out your calculator and you make a division, and you go 700 divided by 380, you actually get only 1.84. So you can see what happens. It means that instead of getting double your force, you're getting not quite double anymore. So the actual mechanical advantage includes the imperfections and the extra effort force that is needed, that happens with every simple machine that we are about to explore. Okay, but now you know how to do the actual mechanical advantage and the ideal mechanical advantage for a lever. In the next video, we'll talk about how we do this for other simple machines.